Oh, well, it's time. So I'm going to just get started. Welcome, everybody. My name is Jim Pivarski. I'm from the University of Chicago's Data Science Institute. And perhaps I should have made a slide about this, but if anyone's looking for a data science position in Chicago, you can talk to me afterward. We have some positions open. And with me is Peter Fackeldey. We will be sort of tag teaming through this tutorial from Princeton University. And yeah, so is there anything you want to say before we get started? No? Okay. All right, and also, you know what I should say? Since this is your first tutorial, welcome to SciPy. Okay, so thanks. So let's get started. So this is the thing that you probably know how to get to. This is from the SciPy schedule. And in this, right up there is a link that goes to the GitHub for all of this. The GitHub has extra information such as the wrong room. We are now in, but you know that, so I don't need to go over that. But it has it just links to the normal instructions on how to use Nabari, but also specializations that you want to click on thinking in arrays, and you want to choose the thinking in arrays kernel and all that. So go here if you need to walk through this. It could be good to set up your Nabari instance while I'm giving my introductory presentation, because it does take a few minutes for the thing to load. Yes? Does it matter what size instance you pick? No, it doesn't. I've tested all of this on the smallest instance. It's fine. It also doesn't matter whether you pick mist or not. Okay. So then when you get into this, you'll be picking the thinking in arrays tutorial, which this actually does a git clone to actually just copy the tutorial in, which I've already done. So now it's in tutorials 2025-0707 SciPy thinking in arrays. We're going to start with part 1. And you can open up the lecture workbook. This is just a small notebook that has everything you need to follow along. But I'm going to go from the lecture, which has like pictures and stuff. Okay. So let's get started. The first topic, the section 1 topic that I'll be talking about is array-oriented programming. And I'm going to present this as a programming paradigm in a sense that, so actually raise your hands if you've heard of a paradigm. If you heard this language has a certain paradigm. Okay, good, a few. Few, but not everybody. So programming paradigms are rough classifications of styles of programming. And sometimes it's said that a particular language has this paradigm. For instance, the big thing about C++ and Java when they were first coming out was that they were object-oriented, and then object-oriented was the big thing. And then there are other languages that absolutely focus in functional programming. So there's just a bunch of these styles, and just to try to, because it's a rough idea, I'm trying to define it by examples. So here's a table of some paradigms, what their names are, kind of what they do, and some of these paradigms have become so obviously the right thing to do that it's become standard. So like structured programming means having a programming language that has constructs like if, for, while, and not go to. This is just, now unstructured programming is no longer a thing, right? Procedural programming, defining subprograms or procedures like functions, and all languages have this now. Object-oriented programming is also fairly ubiquitous. There's some new languages that sort of flaunt the fact that, yes, we do not have object-oriented programming because we disagreed with that idea. So there's some people think object-oriented programming is good, some people think it's bad, but it's a style. It's a way of structuring large programs. Actors, you might not have heard of. Actors is used in concurrency Erlang was an example of this. He sort of made this idea popular. And actually, actor-based programming was the original object-oriented programming. Actor-based programming was made for parallel processing, and then it was simplified into object-oriented programming. So you've sort of seen a specialization of this. Imperative programming is also something that you are very familiar with. This is, I would say, Python's dominant mode. You have statements, and each statement tells the computer what to do. Like you're just giving it orders, one by one. An alternative to this, sort of the big number two programming paradigm, the subdominant one that's been around for decades and always fighting to be distinguished from imperative programming, is functional programming, where everything is a function and you're passing around functions. And so it's not, the computer is not so much following orders as evaluating mathematical functions. You could be strict about that. There's reactive programming, which is something I'm learning now, and it's just sort of amazing to see something that's so different. But here, you set relationships between variables, and they're just always kept up to date. You don't, if you say x equals 5, and then do y equals x squared or something like that, and then you change x, y is changed. And so that's different. Python certainly doesn't do that. Declarative programming, you specify what to do rather than how to do it. These are often very constrained, things like HTML and SQL. There's some, Prolog is perhaps the only example of logic programming, where you basically write down mathematical statements. And literate programming is, you could mix this with any of the above, because you just it's when you put in so many comments that it's more like reading a text and just a little bit of code, which is actually what Jupyter is. So we're kind of looking at it right here. So after that overview, most programming today is structured, procedural, object-oriented, and imperative. These are sort of the dominant paradigms. And then, the favorite example of a different paradigm is strict functional programming. Then if you're going to Haskell or Elm or Elixir or something like that, you're seeing what it could be, what it would be like if it's different. So let's do a concrete example. I think that all these definitions, because they're such loose, vague kind of things, they're best defined by example. So let's see imperative versus functional, those like classic two paradigms. So in this, we're going to do the same problem with two different programs. First, we're going to imperatively compute the square of each element from input data and put the output in output data. So we're going to start with these two NumPy arrays, and the output is zeros, just to have a place to put the output. And this imperative loop is, an explicit for loop, where you say not just which elements to run over, but also the order. The program is not allowed to do this out of order, because it doesn't know if in the for loop you're going to do something that depends on order. And in the for loop, what we're doing is something that doesn't actually depend on order. It's, for each output I, we set it equal to the input I squared, and then we have the output data. So imperative, it should be very familiar. Now, the functional version of that is if you define a function, which is the square of one element, and then you use some functions of functions, such as map, part of Python's standard, built-ins, and you take as an argument the function that you're going to apply and the input data. And so that's an example of a functional or a functor, a function that takes functions. And across functional languages, these names are often the same. Like if you're using Lisp, then it'll also be called map, And then NumPy needs some help if it's going to take data from an iterator, which this map returns an iterator. It's going to need to know what output type it needs to be. But, OK. So Python is not especially friendly to functional programming. For one thing, if I want to make an in-place function, I have to write out the whole word lambda, which is a really long word if you're going to be making hundreds of functions everywhere. What Python has instead, which is kind of like functional programming, but it's a more limited thing, is these list comprehensions. So raise your hand if you've seen list comprehensions. I thought so. Nearly everybody. So this is Python's response to functional programming. It lets you do only a few things. This mapping. So here it's, this inline for loop is a map, and reduction, fx whatever. So it has map and reduce built into this this functional thing. But this would be the more normal way to see functional programming in Python. Okay, so array-oriented programming is like functional, but a little different. And here, if we wanted to square every element in an array, we would take the whole input data and we would just say squared for the whole input array, and we get an output array with every element squared. The thing that's different about this, so the thing that's similar from functional, is we didn't have to write an explicit for loop. Sort of the idea of iterating over collections is sort of built in. But the thing that's different from functional is that nowhere here are we passing it a function. It just already knows about this square. Squaring is one of the things that NumPy has built in. We're not doing anything here that specifies an individual element, right? It's always whole arrays to whole arrays. Okay. I think that this becomes more clear if you work on a larger, okay, so this is the difference I was talking about. I think this becomes more clear if you work on a larger example, because that one-line thing is maybe too simple to really show the difference. So let's take a different, more difficult problem. So suppose what we want to do is we want to calculate gravitational forces between n planets. This is more complicated than a single formula because since you have n planets, you have to calculate n times n minus 1 forces. So it's a bit more complicated. Let's start with an initial setup. The imperative version, which doesn't quite fit on the screen because imperative can be kind of verbose, is that you want the total force, so you've got a place to put it. And then you have these nested for loops. This is the n times n minus 1 iterations over all these planets. And then you just have to, you have to do things like make sure that you're not calculating a gravitational force of a planet on itself, which if you were to just calculate it would be infinite. And so you don't want to do that. Also, you wouldn't have a place to put it, this output. And then you just, you go through all of these individually. This is I think, something that most everybody here could do. Like if you have the formula for gravitational force, you could sit down and write these for loops. This is one of those things that is like a basic programming problem. Okay. Now the functional version of this, now we're going to see how it's different. Now that we're getting a bit more into a more involved problem in functional programming, we have to go to some not built-ins but still standard libraries in Python in order to get the things we need in order to do this. We're going to need reduce, which in Python 2 was built in, but in Python 3 they pushed it off into a library. And combinations, which is the sort of thing that really ought to be in a library. And the combinations is going to do the n times n minus 1. We have all these functions to do all the different parts of the problem. And these could have been lambda expressions, except that would make it very messy. Most of the work is done here in this list comprehension. And here's combinations. This is what's going to give us these pairs. Okay. Now the array-oriented version of this is considerably shorter than the rest. One of the things that you get out of array-oriented programming is conciseness. Sometimes it can be too much conciseness. So even though this is a really short function, it's pretty dense. You would have to, the fact that it's short doesn't mean that it's quicker to understand or simpler. It's sort of like this solid block that you would need to sort of pick apart one piece at a time. Like if you're given this program and you're trying to understand it, you're probably going to want to break this out of the function and run each line individually and look at the outputs and see what it's doing. So conciseness can be a blessing and a curse. But anyway, now that we've written these three functions, I just want to verify that they give the same answer. Yeah, they do. And for fun, we're going to visualize them. I picked this problem because it's fun to look at. Fun to look at the results. So I'm just going to evaluate through some stuff for plotting, for taking these forces and moving all the planets by a step, and then plot everything. So that I'm going to evaluate forward. So that with different setups, we can just watch the planets run. So, sun, the Earth, and the Moon. Yay! Going around. Stop. The three-body problem. I made this when the show was coming out. There are solutions to the three-body problem that are really cool. Mathematicians have cataloged these. If you set up the initial conditions just right, you can make like figure eights and stuff like that. And then absolute chaos, where we just make a bunch of random planets and let them go. Yeah. Anyway. Okay, but more seriously, let's time it. That's the main thing I want to get to. The imperative came out at almost a second to calculate one step. So 900 milliseconds. The functional is still going. I'm a little bit worried because I know that this one is a bit longer. I can actually talk about it. Python is not optimized for functional programming. So while it might be a good way to organize your thoughts, Python has all these stack frames and everything, a lot of overhead for going into each stack frame. So if you have lots of functions, it gets worse and worse. And then the array-oriented was 50 milliseconds. So compare that to the imperative. Was this a factor of 20 faster? So this is the reason that we often do array-oriented programming in Python, because we want to use Python for scientific applications. We often need to do a lot of number crunching. We need to do it fast in order to, make something run in a lunch break instead of overnight or for a week or whatever it is. And array-oriented programming gives us this, especially in Python. And the reason is that for every line of code that you go through in Python, there's significant overhead, because Python has a virtual machine. Python doesn't do type checking up front. It doesn't compile code that doesn't need to check its types at runtime. So Python needs to check its types at runtime, and all of that. If you're going through 1 million elements in an array, on every element it has to check, is this an integer? Oh yeah, it is. Okay, next one. Is this an integer? Oh yeah, it is. You can keep going. And that just takes a lot of time. Whereas the array, what am I doing with this table here? In the imperative forces, functional forces, array forces, this is the number of lines of Python that we were looking at. And then if you translate this to actually what does the Python interpreter go through, Python interpreter goes through byte codes of Python. It takes your code, compiles it down to something simple, that byte codes that look like machine code, but actually are much more high level than machine code. And the Python interpreter has to go through each one of these byte codes and interpret them one by one. And then the big thing I should have perhaps led with is the scaling. It has to do all of these bytecode instructions for each of the n times n minus 1 calculations. So the thing that scales large, it has to do all this work for all of them, for every element of the array. Whereas the array forces might have just as much or more Python instructions, but it does those once up front. It does those once for the whole program. It does this 103 Python bytecode instructions once. And one of those bytecode instructions is do a giant precompiled thing on everything in the array. That's the key thing. The key thing is how it scales. So I've been talking about bytecode instructions. We should look at them. So like if you're doing some function like x plus x, you can actually look at the Python bytecode instructions with dis, the built-in disassembler. This is what I'm talking about. This function starts into a function. There's a bytecode for that. Loads x, and then runs a binary operator on it. This binary operator, these are the things that the Python virtual machine is stepping through. This binary operator doesn't know anything about what x is, and it has to check every time. I hope this is okay. Am I still all right? Let's find out. Okay, so array-oriented programming is a good mental fit for doing data analysis. This is a big plot that I've been just adding languages to as I've been collecting all the languages that are array-oriented. Many of them you've not heard of. Many of them are very obscure. A few of them, maybe MATLAB, R, and I would say that NumPy and not Python is the array-oriented part. These are, like, key thing about all of these languages that almost all of them are data analysis languages. Almost all of them are intended for doing interactive data analysis. So they're all like interactive languages, and they all are focused on data analysis. And that's why this is part of what I'm saying that array-oriented programming is a good fit for data analysis, because it's interactive, as data analysis is, and each step does a large amount of numerical processing, which is what you need in data analysis. So consider, oh boy, do I really need to reconnect? No kernel, thinking arrays. Please? Yay, okay, good. So think about it. Which of these is the most idiomatic pandas? So this one, where we're going to, do some selection and then square something. Or this one, where we're going to use an apply and pass it a lambda. Or this one, where we write for loops over the pandas data frame. So actually, show of hands. Who thinks that this is the most idiomatic pandas? So raise hands. A few. Who thinks this is? Right? Mm-hmm. And then this one. Yeah, that's about right. Pandas is, this is array-oriented. This is more functional, I'd say. And this is imperative. Yeah, Pandas is not imperative. If, you would really be slowed down in your data analysis if you had to write these for loops. Pandas is kind of skirting the border between array-oriented and functional. So yes, you were right to raise your hand that this is a thing you would see in idiomatic pandas. Pandas is skirting the border because often when you're using pandas, the data sets are not so large, and you can sort of get away with some functional programming. But you'll find that something like this is much faster than something like this. Okay. So, I wanted to, so here we are pretty much at the end where we would move on to the first project. And then just before that, I have a small example that I think that, let's do this and we'll catch up time later, because in the first project, I'm going to ask you to do an array-oriented project, but I think we should do a simple one together first before you go into the main project. So here's the problem. And this is something you want to do in your workbooks. So everybody got their workbook up and running, and it didn't just disconnect for some reason. If it did just disconnect, try to reconnect. And you can do that up here. This is where the kernel is. All right. So you want to compute the length of a curve whose xy positions are given by arrays x and y. So this is a very typical sort of array-oriented problem. So first, I'm going to create them. We don't use t, t is just for defining x and y. I'm going to bring in matplotlib so we can take a look at this thing. It's a pretty curve. And the question is, we want to just find the length of this curve. And the way that, so a hint going into this is that the main steps that most array-oriented problems have is you want to slice the arrays to align relevant parts. You want to map a single mathematical operation across all elements of equal-sized arrays. We've already been seeing that. And then you often want to reduce arrays to scalars. These are 3 typical ingredients to an array-oriented solution. And then I'm going to give you this, that the formula for the length of a line segment is square root of x squared plus y squared. But then the problem is you want to find the length of the whole line, so you need to find the length of all the segments and add them up. So I'm going to give you just 5 minutes. You can use this space. Actually, what I'll do is I'll give you till 8:30, which is 3 minutes. Sort of round everything off. So let's just go at it. Just go at this. It'll be 3 minutes and I'll give you the solution. I don't want to break this up, but how's everybody doing? Raise your hands if you got it. Yep, no butts on. All right. Mm-hmm. Okay, so I'm going to just walk through it, and then you'll have more chance to practice on sort of a bigger problem in the project. So let's start. Actually, I'm going to also go through the thought process, which is sort of starting from the inside and working out. So this length of a line segment, this is sort of the inside of the problem. So stop that, whatever it is you're doing. Okay, so first, it's not unusual for me to just look at things. Okay. The fact that I can do this, working it up little by little and looking at not just a single result, but the whole result with every time, this is sort of the data analysis flow. The reason why this form of programming is good for data analysis. It's like, okay, we got that. Now if I do square root, now I'm kind of asking myself, I'm taking a square root, are any of them negative or something? And I should get a warning at this stage. All right, so this, that's a bunch of lengths. And actually, I was doing something wrong here because here I was finding the x squared and x squared plus y squared. These are not the lengths of these segments, which are delta x squared plus delta y squared. Yep. These are the distance of each of these points from like an origin, which is completely different. But I wasn't thinking that, and I'm just sort of thinking on my feet. First thing we're going to need is the distances between pairs. So we've got all of x, and I want to find the distance from here to here, and then from here to here. Okay. So the way that I can do that is if I had an array which is all of this, everything but the first, minus all of this, everything but the last, that would give me all the differences in x. So I'm going to have to slice here. All but the first looks like that, so we don't have the 0 anymore. And all but the last, we know Python indexing conventions. So there we get differences. It's interesting, we don't see any e's in this anymore. These are no longer big numbers. Now they're all small differences. Okay, so that is the delta x that I actually wanted to square. Okay, that's looking good. These should all be positive. And then we want to do the same thing for y. Oops, near you. Okay, x squared plus y squared. Okay, now we get the square roots. All right, that's all looking good. So now we have an array of, line segment lengths. Now the last thing that we need to do is add them all up, and NumPy has a function for that. It also has a method you could use either way. So that's it. The length of this is 21.23 something. And that, I wanted to show that real time, especially when I had not been thinking, because that's sort of the way that you go about these. It sort of feels like you're going from inside out. So now, the thing that you want to do is open up the project. This project explains itself. You're going to be computing, thinking in arrays. You're going to be computing Conway's Game of Life. And you're going to do it array-oriented style instead of imperative style. And yeah, usually this will be presented in an imperative way. So you read about it. Actually, first of all, everybody pair up. Everybody, find your neighbor. Bring your laptops close together so that you can work on this project in pairs. It will really, I think this will go much better if you're all talking. Let this room be loud. It's fine. And sort of work your way through it. And we're going to have 15 minutes to do this project. So it's 8:35 plus 15 is 50, 8:50. And then we'll have a 5-minute break. Okay? Okay. This one. Yes. 5 minutes. I wanted to let you know that it's 8:50. I gave 15 minutes to work on this. Now we have a 5-minute break. So you can get coffee or whatever, or you could keep working for 5 minutes if you're like in the midst of it. What we're going to do immediately after the 5-minute break is I'm going to go through solutions. So in 5 minutes, I'll show you solutions.
Better to dismiss this and reconnect with the kernel or the environment.
We're good.
Okay. It's I wish there would be somehow we can turn this off.
With a little thing in the corner?
No, I mean restart and dismiss every 5 minutes.
That's well, of course, yeah. It's broken.
It's pretty unfortunate for a lecture.
Okay. Now it's 8:55. That's what it said. It said that's the end of the 5-minute break.
Yes.
So I'm gonna get into the solutions to. Oh, yeah, put that. I'm away from the microphone on purpose.
Yeah, well, just for the records, they were.
Okay. Okay. I hope you're having fun. But we're gonna have to stop now because I want to show solutions, and then we can get on to other topics. So I'm going to go to the solutions notebook, which you shouldn't have been looking at. Thinking in arrays. Yeah, and let's just look at it. All right, so yeah, I'm just going to scroll past. Oh, at this zoom level, this thing looks terrible. Okay, so the just pulling up the definitions again. Should be able to just watch this thing crawl forward. Yeah. All right. So the solutions, I'm going to go through several different solutions because there's not just one way to do this. The first one I'm going to talk about is going to use a special function in NumPy. It often happens that you'll be working on something for a while and then you just find out, oh, there's a function for that. This is almost a case like that. The special function is np_roll, and I'm going to show what it does with, this is supposed to be an anime eye. It's supposed to be like an eyeball of an anime character, so that we can roll it to the left. See, the pupil went that way. Roll it to the right, and look up. And what roll is doing is it takes the original array, the axis determines which direction we're going to roll, and this determines how much we're going to roll. +1, -1. And if you roll too far, it just sort of loops around. So what we need to do is we need to calculate the number of left neighbors and right neighbors and above neighbors and below neighbors, the 8 neighbors of each pixel. And we can do that by taking the original array of the number of microbes in each cell and number of, or is it just 0 or 1? Whether or not a cell has a microbe in it or not, the 0 or 1 microbes in each cell, and rotate it up, do a difference, and now we found the number of above neighbors. Rotate it down, subtract, and then we found the number of below neighbors, and do that for each of the 8 directions. So we can get left neighbors, left or right neighbors, just by rolling and adding. And then to get all of the 8 neighbors, that's 8 rolls. So in this thing about scaling, the thing that does not scale, the thing that we've got to call a bunch of Python functions, do a lot of Python bytecodes, is for each of the 8 rolls. That's, for this number 8 is something we're just going to have to do again and again, and that's the, we could even write a for loop for that, and it would not, and then you've done 8 things. But 8 is a small number compared to the number of cells in this grid. The number of cells in the grid is the thing that gets that the compiled function runs over. So it's sort of a division, a separation you want to make. So you can roll it each way and find out how many northwest neighbors, north neighbors, northeast neighbors, and then just add them up and you got all the number of neighbors. And then from there, the number of survivors, births, is just a matter of computing a formula. And computing a formula is the easy thing to do in array-oriented programming. And then we can walk with this. Well, I haven't defined it. It's up here. Here we go. You can just see it run. And we're walking along. Okay. So if you time it, I'm not going to run these because they will take some time. I don't have the number to compare to, but it's faster than doing it with pure Python for loops. Now, it's going to feel unsatisfying if you just didn't happen to find this function in the library. Did you need to just know this? No, you didn't. You could, compute it manually. You can do it with slices. And these slices are very much like the slices that we use to find the length of the length of that string, that curve. And we just have to do the slices in every direction. The left slices, we are, to shift it to the left or shift it to the right, we are slicing the first dimension, just shift it up or down. I got that backward, but you get the idea. So here's the same thing without NumPy roll, and it's just slicing. And I've lined up all of the I've lined all these things up in order to show the logic of it. And unfortunately, black and other code formatters will hide that sort of thing. But I think it's good to be able to just line these things up in order to see what we're doing in each case. We're for the northwest, north, and northeast neighbors, all of these are north, and so we're doing the same thing in the first dimension, and then different things in the second dimension, and so on. Yeah, and that was not taking any boundaries into account. And I made this problem so you don't have to worry about the boundaries. You can run this for 200 iterations, and it doesn't touch the boundaries. And that was just to simplify the problem. You could get the boundaries right, and that means more bookkeeping, more careful. What you can do is you can actually make a padded world, take the whole world and increase it by 1 pixel in both directions, do the calculation there, and then run around and catch, and look at the edges and take care of the edges manually. All of those extra manual steps, those extra lines of code in here, is the stuff that makes the number of Python instructions scale. But that's still small. You're still talking about 8 things or 4 things, whereas the grid itself is hundreds or thousands of things. And then there's the sneaky solution. Actually, how many people tried to do the convolution solution? A few. How many got it? Yeah? Okay. This is another thing that often comes out of array-oriented programming, is that mathematical knowledge is helpful. If you just if you're familiar with convolutions and you're looking at this problem, nothing about Conway's Game of Life says I'm a convolution problem. It's posed not as a convolution problem. But if you look at it, you realize that in order to find the number of neighbors here, that is a convolution with this kernel. With convolutions, I'm not going to go into what convolutions are and how to do them, but if you're familiar with convolutions, it's a matter of you have to find the small kernel, the small matrix kernel that does what you want, and this is it. And this is very much, you feel like a mathematician if you do this kind of if you solve it this kind of way. But yeah, it can be done. It can be solved with a convolution. Okay, so those are the solutions. Let's move on to the next topic. Or actually, any burning question about this before we move on? If not, then let's talk about whatever the next thing is I have to find. I'm going to, you probably want to do this also. I'm going to shut down all of these so we don't run out of memory, and move on to part 2. And this one doesn't have a workbook, so we just sit back and enjoy the lecture, and we'll try to spend most of the time on the project. Okay, thinking arrays, and pluck that up 1. All right, so now that I've just been talking about array-oriented programming and how great it is, now let's talk about the limitations of array-oriented programming, because every technique has its pluses and minuses. Everything has some kind of drawback. So let's talk about them now. So first of all, I was introducing array-oriented programming as a way to get good performance out of Python. Or I guess I didn't say it verbally, but also GPU programming is a very array-oriented paradigm. And then and you would be thinking in arrays even if you weren't using Python, if you're doing GPU programming. Okay, but after having said that, it is not the best performance that you could get. And let's illustrate that by taking a formula, this exactly the sort of thing you would want to calculate at scale. Exactly the sort of thing? I don't know, it's a formula. And it's a reasonably complex formula. And now we have a whole bunch of arrays, and the idea is that we're going to take these arrays A, B, and C, and we're just going to put them in here. If I was doing the NP ND array, doing the that's what we want to do. Okay, so now first, when we compare it to the imperative, the NumPy solution is going to be much faster than the Python for loops imperative. That's something that we've already established. But then something we're going to see that'll be maybe a surprise is that there are other ways to do it that are faster than NumPy. And that's what this is going to be about. All these timing things, I should always run them before I start talking. Yeah. So we got 10 seconds on doing that with for loops. And 1/10 of a second doing that with NumPy. So great, that's a big win. But then, 180 milliseconds versus 30 milliseconds. This NumExpert is doing something that is much faster than the NumPy. So what is it doing? Actually, we shouldn't be, with performance things, often the question, if you got a fast thing and a slow thing, the question is not what is the fast thing doing right. The question is usually what is the slow thing doing wrong. That's kind of usually the best way to frame questions about performance. So let's see what NumPy is doing wrong. Each of these mathematical operations, so the plus, the times, the square root, and all, it performs that operation over the whole array. So we gave it arrays A, B, and C, and it has to run over A, B, and C every time it does every one of those calculations. This function, this pedantic quadratic formula, is functionally equivalent to what the easy-to-write formula was. What NumPy was doing when it saw the minus b is it makes a new temporary array. It has to allocate the memory. It has to run over the original arrays and run over the output array, and touch them all in order to put negative b into this new temp1. Then it has to do squaring b and put that all into temp2, et cetera, et cetera. And it does delete arrays as soon as they are no longer needed. The reference count will go to 0 and this array will just disappear. But this is basically, so this is it. This is what NumPy is actually doing when it's computing that formula. And we can see that that's what it's doing by, running a timing test. They're roughly the same. There's not a big factor 2 or anything between them. 150 milliseconds versus 150 milliseconds. There's a caveat that NumPy is sometimes able to fuse this, and in some years when I present this, there's a difference between these, but new versions, the different versions of NumPy get smarter or dumber, and they performance numbers jump around, but right now they're really making my point, which is that they're both the same way of doing it. So NumExpert, on the other hand, takes that string and does something kind of like compiling it. What it actually does is something a bit more like what a regular expression does when you do re.compile in Python. It takes the expression as a string. It's got its own language. It parses that string, and it makes a small, fast virtual machine that only does math, and so it's faster than the Python virtual machine, which does a lot more than just math. That virtual machine is also type aware, and so those are all things that speed it up. So NumExpr almost compiles it. It does something that's very similar to compilation, but we can go a little bit further, and there's this thing called NumPy. It's a library that when you import it and you use numba.vectorize or numba.jit, JIT for just-in-time compilation, it will actually compile. And by actually, I mean it takes this Python code and it replaces it with LLVM IR, LLVM intermediate representation, which is a step toward the same compilation that the Clang compiler uses to compile C code or C++ code. So what NumPy has done here is it's really compiled the thing. It's compiled it as much as if this were a Python function. Sorry. It's compiled this as much as if this were a C function. So if I remember the number from above, NumExpr was 30 milliseconds, and the really low-level compilation we get down to 20, 21. JAX is a completely different kind of compiler, and we'll be seeing more about NumPy versus JAX. They are so different that it's worth knowing about both and maybe using both. It's not really a this versus that. I guess I could say in a nutshell what they do differently. NumPy looks at this Python function, and if it can replace it with compilable LLVM intermediate representation, it will do so. If it can't figure out what to replace it with, it'll give you a big compilation error. And when you're working with NumPy, you do often have to go in small steps in many tries in order to get through all the compilation errors. And what you're writing is imperative code. If I were to use numba.jit, we would actually see a for loop. I think we're going to do some examples like that. JAX is quite different. When you do jax.jit, it walks through this and it builds up a sort of a list of expressions. A list of expressions that when you get to the point where you're actually going to run it, it compiles this with a different tool chain, XLA. This is not like Clang compilation. And the main difference between the two, from your perspective, is that when you're using NumPy, you get to write for loops and they're fast. You get to write imperative programming. When you're doing JAX, you get to write array-oriented programming and it's fast. Okay. And this one, this one wasn't fast, but that's performance things. Slightly different example, run on different platforms. They're different. Actually, this is a worse number than I got in any of the testing. So maybe if I just run it again, maybe we might get something better. We'll see. But anyway, I made a bottom line plot, sort of scorecard. I'm just waiting to see if this... Another thing about performance numbers, you got to make sure that you're using a large enough sample that you're actually seeing the part that scales rather than the overhead. And you've got to run it many times. Sometimes the first time through can be much worse, which is actually why in these examples I did a first time through here before starting the timing. No, this is still 100. This is not so great. Yeah, okay, I guess I saw that in some of my test examples. But basically we have something like this. Pure Python is always orders of magnitude worse than anything else. We get the first big jump by switching it with NumPy. Then if we do things that fuse these operations to make sure that we don't run over the same arrays multiple times and have the CPU need to fetch it from RAM into the CPU, which is an expensive operation, many times, then we can get better. You say with like a fast virtual machine or like actually compiling it. And sometimes JAX is much faster than NumPy, sometimes NumPy is much faster than JAX. No, remove the word much. So sometimes, they're often like neck and neck. One will be better than the other depending on the situation. Okay, so there's the speed, and then the other limitation for array-oriented programming is the expressiveness. Some things are just very difficult to express in array-oriented form. Most of these algorithms that you're going to have trouble with are the ones that include the words iterate until converged. So in order to illustrate this, let's look at computing two different kinds of functions. First, a good function and then a bad function. A good function that is easy to vectorize, and then a bad function that's hard to vectorize. So suppose that the SciPy library, which just does all these things for you, didn't exist, and you had to calculate this function. In the old days, you would get this book, you read it, and it's Fortran, and then you translate the Fortran into Python, and it looks like this. It'll say that this is the best way to calculate that log of gamma, which nowadays are just sort of encoded in the Python, in the SciPy library, and you don't have to think about it anymore. But okay, so this is a good function to vectorize, which we'll see in a moment. But first, I'm just going to illustrate that, what this function looks like. I've defined it, and here I'm filling it with a list comprehension, so I'm not using this in vectorized mode yet. I'm just computing this. I'm just computing this function as a scalar Python function. So right now I'm using it this way, and in a moment I'm going to want to use it this way. Okay. And I have to verify that it's the same as SciPy, just so that we're not just so we know we're not doing anything wrong. It is. Now, this function is easy to vectorize. We could take the array XS and pass that in as an argument and get an array out. It just happens automatically because let's look at the function. If X is an array instead of a scalar, okay, then every element in the array is we're going to add 5 to it. Then we're going to do this to it, but we're just applying mathematical operations to every element of the array separately. And then, we have a for loop here, but again, this is not one of those for loops that scales with the elements in an array. This is a for loop that goes over 6 things. I could have written 6 statements, kind of like we had the 8 roll statements. This kind of for loop doesn't hurt when you're doing things at scale. And so it's just updating this series variable, and then we return something they're all formulas. It's basically, you could write these down as closed form mathematical formulas. That's all great for vectorization. It's great for vectorization without even having to think about it. You just take a scalar formula, put it in arrays, and it works. Now let's look at a bad function. This one, just another one of these random, special functions. But this one is going to be bad to vectorize because it has a loop over, at most 100 iterations before it gives up. And so this is one of those iterate until converged things. If once this criterion is met for scalar arguments, then this function returns with the result. So this might only go 30 iterations and then find its solution and return. We can do this as list comprehensions because we're just going through, because these are being called on scalars to see what these functions look like. Okay. And they are equal to the SciPy equivalents. But if we just try to drop an array into that X argument, it doesn't work because it gets to this line of code, which is supposed to, it's an if statement, and at that line of code, it's supposed to determine if this expression is true or false, and then either go into this body or not. And with arrays, maybe some elements satisfy that criteria and other elements don't satisfy that criteria. So what's Python going to do? There's nothing that it doesn't know what to do. So NumPy has anything that looks like that just become an error. If you use NumPy a lot, you've probably seen this message a lot. The truth value of an array with more than one element is ambiguous. Or maybe you've seen that before. Actually, raise your hand if you have. Yeah, I thought so. And it's because you run into these problems. If you're writing a function that would work with scalars and has if statement to break out of a loop, you just can't do that with arrays. This is a limitation of array-oriented programming. Okay, so let's quickly look at two quick ways to work around this, and then we'll get to the project. One is suppose that we're going to say, let's go 100 iterations and not even check to see if we've converged or not. And also not even check to see if after just 30 iterations we're converged. Who cares? We're going to go 100 anyway. This is the easy solution. We know how to write that. And by doing this, this has made it, this is checking with SciPy, it happens to be, since it happens to have converged, these are the right results. But this could go wrong if after 100 iterations it hadn't actually converged. It would give you an answer which is wrong. Something to be concerned about. And this version of it tries to do the bookkeeping, tries to keep track of what's converged and what hasn't. It has an extra array of Booleans to say, it's an array, and in each element of the array has this one converged yet? Has that one converged yet? Has that one converged yet? And it tries to only update the ones that haven't converged, so it doesn't do extra work once you've gotten to the final result. And that all is also correct. But now, which one's faster? It turns out that the easy one was faster. You might think that if we do some extra work to try to prevent the computer from having to do extra work, like compute after it's already converged, we're going to save some time. But no, our efforts are not always rewarded. In fact, they're often not rewarded. With array-oriented programming, it's often better to just do the simple thing and just not keep track of which ones have converged and just go enough times. I don't know if I made a mention of this, but yes. Has anyone used PyTorch? Raise your hands if you have, which I thought quite a few. You notice that in PyTorch, we're often doing like for epoch in range some big number. This is doing a fit, and it's not checking to see if the fit has converged or not. And this, I feel like, is just a concession to the fact that we're going to be using array-oriented programming, and we're just going to not worry about this question of iterate until converge. We're going to go for a large number of times. Sorry. We're going to go, some large number. Check afterward to see if the whole thing is converged. We're going to look at that loss function. We're going to, use a test sample and all that as sort of workarounds for, what in the old days when everything was scalar computations running on a compiled language, it would internally check to see if it's converged. But anyway, so that's where you've probably seen this before. Oh yeah. Any questions about that before we move on to the project? Okay. I will check the time. Here's project. Don't go into the solutions until you've tried it. And again, pair up. Find a partner to work on this. Let me check the time and say when we'll be finishing. Should be an hour 35, so that's only 10 minutes? No, I'm going to give you full 20 minutes. This is a significant project. I want to give you full 20 minutes. 9:25 will be 9:45. We're going to go till 9:45. Then we'll take a short break and we'll look at solutions. So yeah, go ahead and talk. Make it loud in here. It's fine. Stays alive. Okay, we're at the end of the 20 minutes, but just as before, we have a break now. 5-minute break. You can get something or you can keep working. So 9:50. Okay, how's everybody doing? Ready for solutions? Mm-hmm. Okay, let's go see. So this problem, oh darn, I clicked it away. Can I get it back? Yeah. Yeah. This problem is the tree by itself, doing this tree traversal, is kind of a intro CS kind of problem. You know, walking down trees is a pretty common thing where you would have this tree data structure where you have a left node and a right node, and you have to decide whether to go down the left node or go down the right node. It's all very classic CS as a recursive function. It's like, this is perfect as a recursive function. Now that's exactly what we're going to not do in this case. This was the thing where, can I find it again? You know, the classic CS problem of walking down a tree. I just have this mental image, which goes down. You know, do I go left? Do I go right? Do I go left? Do I go right? And darn. Whereas what we're going to want to do here is a bit like multi-plinko. It's got all these beads, and each one of the beads, you know, is still going to be making a left-right decision, and that's kind of the this part here from top to bottom. These are the Python for loops. You know, first we'll decide what everything does at the first level, then we'll decide what everything does at the second level, then we'll do what everything does. Look at what everything does at the third level, but we're going to do that for lots and lots of data at a time. So we have a lot of data coming in, and some of them are going left, some of them are going right. Lots of data coming into the second level. Some of them are going left, some of them are going right. So it's the sort of thing that is a sort of problem that, on the face of it, doesn't look like something that would work in a vectorized way, but then you think, I'm not vectorizing these decisions, which every level depends on the previous. I'm vectorizing across a whole bunch of things all going through. Anyway, you've been working on it for a bit. Let's look at it. So to start with, I'm just using scikit-learn to get a tree. Just decided to make this old school machine learning problem, just so that we have a nice tree to work with. There's the decision that the decision tree is making. You know, it's all straight horizontal and vertical because at each level it's deciding is X greater than something or is Y greater than something, and deciding which way to go based on that. So we get a decider, a classifier that is dividing up the plane in this kind of straight, horizontal and vertical lines. Anyway, old school machine learning. So there are a few different ways of evaluating this, and where the problem is just to evaluate the tree, taking the tree as a given. There's an immutable way in which none of our arrays are changed in place. We always get new arrays. And then there's a mutable way where we will be replacing the arrays in place. Sometimes, often, doing things mutably, replacing the arrays in place, is faster because you don't have to allocate as much memory, and you're looking at the same spot in RAM, so that might be something that the CPU already has cached. So changing arrays in place can often be faster but lead to subtle bugs. When we're getting into JAX in the next section, JAX just flat out does not allow it. JAX is immutable everywhere. So we want to be able to solve things immutably. We want to be able to write down immutable solutions. So we start with I'm just going to set up a problem that, a small problem. By the way, this also is a good way to go about solving larger problems, is to make yourself something that has the same structure as the large problem, but only a few elements in it, so that you can walk through each step and then ask yourself at each step, is this what I wanted to happen to these 2 or 3 or just a handful of elements? So in doing that, these are the positions. So I'm making just 3 things at the top, 3 XY points at the root of the tree. And then I'm going to step through the tree manually and figure out what it is I want to do with them at each step. So first, setting the array indices to 0 is to say we're going to start at the root of the tree, because the tree is described by an array, and in the tree, array index 0 is the root of the tree, and then that array of indices says at each point where the left branch goes and where the right branch goes. So it goes to different indices in this big array. So it's an array that represents the tree by having the array contains indices of itself. And that's how it walks through. Okay. So the first thing that we do is we set everything at the root by setting the array indices of these 3 XY points to 0, 0, and 0. And then we use it as an array slice to find out what features are at the root. 0, 0, and 0. And it happens to be 1, 1, 1. We ask, what are the thresholds at that same place? Each of these arrays. The features arrays, the thresholds arrays, the children left and the children right. Just looking at what we have at that root indices, 3 times, and you notice what's coming out of each one of these is the same value 3 times, because we're looking at the root 3 times for each of our XY points. Right. So now, let's since we're still figuring out the problem, let's say that I ad hoc decide that the first should go left and the other 2 go right, and I'm just making that up, right? I looked at the structure of that array, and I saw that the going left from the root would be going to number 1, and going right from the root would be going to number 136. I'm just stepping through this just to make sure that I understand how I'm going to go about this. Ask for what are the features there. They're again 1, 1, 1. And ask for the thresholds. Now the second 2 thresholds are different from the first. Children left and children right. The left goes to 2. The right goes to 69. And then for these other 2, the left and the right go to 137 and 146. So I'm just I'm sort of walking through what I want the eventual function to do, but I'm doing it manually as a way of figuring stuff out. And this will involve a lot of trial and error, right? Going through this. So now we got kind of the idea of how we're going to put it together. Array-wise, the ones that, we also need to know if it's going to stop. If the left children doesn't go anywhere, like if the left child node is a leaf, we're not going to go anywhere, that's encoded in the array as a -1. So we're going to ask, are things greater than 0? And since we're doing this for all of the elements in the array, we do it as one of these element-wise operations. So this is going to tell us for all of our Plinko beads, which ones are stopped at the left. Which ones at the left have reached a leaf. Which, by the way, is an iterate until converged. When you reach a leaf, you've converged. And what should we do if we have converged? Well, we're going to be running code on everything. We're going to be running code on everything, including the ones that have converged. They have to stay there. So we're going to make them, just circle around, just sit in place. Keep going to itself when it has reached a leaf. And everything else that hasn't reached a leaf can keep going. Okay. The ones that will be choosing to go left is this expression. Explaining this expression, this was in the first hint. Here, this part is asking for an array of 0, 1, 2, 3, 4, 5. This is the first hint. It's a two-dimensional slice in which we take every member of the first dimension. So the comma. Square brackets is going to be selecting elements. The comma separates what we're doing in the first dimension from what we're doing in the second dimension. In the first dimension, we don't want to do anything special. We would just want to take one of each, right? In the second dimension, we want to take the output of this features array, which is 0 if x, 1 if y. And so this two-dimensional slice is what which tells us which way to go. So here I'm doing a bigger example. This one has 1, 2, 3, 4, it says 10 xy points. So the first example was small and simple for me to figure out a few of the basic steps. Now I'm going to need a bigger example in order to figure out what to do more generally. So, I'm changing up the initial fake examples. So to look at this, what it's doing in each step, so this is a bunch of xy points. The first dimension is 0, 1, 2, 3, 4, 5 because I want to touch every one of them. And the second dimension, let's say that my features array was, x, y, x, y, x, y, x, y. Doing this slice, this two-dimensional slice, will pick 0, 1.1, so here it's coming into this, and it's picking, okay, the first 0 was coming into this and picking the left, that 0. The second is coming into this and picking the right, this 1. The next one is coming into this and picking the left, this 0. So you make examples like this that are easy enough to see what's happening, not just random floating point numbers, which are kind of hard for the eye to sort of pick out. Make these very contrived floating point examples in order to help yourself solve this. So what I'm walking through here is like a solution technique, how you think about making a solution. Okay. Instead of using arrays of integers, we could have done it with arrays of booleans, but you can read about that offline. So now, sort of pulling more of these things together, let's take let's say that we're starting at the point where we already know whether we're choosing left. Yes, we're choosing left. No, we're choosing right. Yes, we're choosing left. No, we're choosing right. Just making this contrived example. And these are the left indices and the right indices, and we can see that numpy.where, choosing left as a Boolean, yes we do, no we don't, yes we do, no we don't, we'll pick from the left indices or the right indices depending on whether that's a true or a false. This numpy.where is kind of like a vectorized if statement, and we use this a lot, so this is a good one to know about. Okay. The last step, which I already alluded to, is that some nodes don't have children. You get to a left node and it's -1, and we have to stop and just sort of have a holding pattern, like an airplane flying around and around an airport, never landing. That's what we want to do if we have children, we're going to do this numpy where, and if we don't, we're just going to sit there and just, go from this point to itself over and over in order to keep it from moving, because this is the final answer that we want. We just need the other array elements to converge. So putting that all together, the function looks like this. It has all the things that I had built up by working it through with small examples and testing my intuition and trying, seeing what the results were. First, we want to decide array-wise who has children. which of the Plinko beads are at a leaf or not. Get all the features, all the thresholds, all the left indices, all the right indices. Then which ones will be choosing left will be first for each of these positions. Am I looking at the X or am I looking at the Y? And this will return either the X or the Y. And then I'm asking, is it below the threshold? So then, if we're choosing left or choosing right, we go either the left index or the right index. And if we are, if we don't have children, we stay there. So that is all of this. This is, now, let me just say that this was the hardest problem I could think of. This is the hardest thing to do in an array-oriented way that I could think of from trying lots of different problems. This is really pulling all the stops. This is, you really have to think differently to do this, and sort of this walkthrough of how do you pull this together will help you solve problems like this in the future. This was not an easy problem, just to be clear. Yeah, and then at this point now we can predict one step. All of that function there is predicting one step down the tree. So like when we're at the root node, we run this and then we find out where everybody is at the second level, and then we run this and we find out where everyone is at the third level. Then we run this to find out where everyone is at the fourth level. So we have to run this as many times as the tree has depth. So if it's a depth 10 tree, then we run this function 10 times in order to move all the Plinko beads into where they're going to land. And if we didn't know how deep the tree was, that would be a problem because we have to run this until everybody reaches the bottom. Maybe if we didn't know how deep the tree was, we would keep running this function until the array doesn't change. That could be a way to find out if you get to the end. Okay. Knowing the maximum tree depth, we know to just run it 10 times, and then we have the full function. Okay. Making a plot with this. Now we're just running it, and we get the same picture to show that we know how to walk down this tree. The function is successful. There is in these solutions a modify in place solution where we're not using np.where to very carefully make sure that we don't clobber our previous arrays, we don't write over the previous arrays. The modify in place solution will use slices to change the original arrays. And at each level, we have only one array that we're changing in place until you get to the bottom. I'm not going to do that in detail. Somewhere in here, there's also a numba solution. I've lost track of where it is, but that's numba is doing it the traditional way, just doing a recursive function, the way that you would learn in a CS class. And that's to do a time comparison. Here it is. Yeah, compiled single tree traversal. This is like the classic way. If you have children, then you figure out where you're going to go, and you have an if statement here. You get to ask a single if statement. Am I above or below threshold? You don't have to do np.where, and then you return differently in this recursive function, depending on if you go left or right. Okay. And I think I also have a JAX version where I just took the NumPy version, and because JAX is array-oriented, I just do the same thing with JAX. And that all is to get down to the final timing results, because this kind of shows what we did this all for. Recursively walking down the tree in Python, making the choice go left, go right, just with Python for loops is, of course, terrible performance. But then, perhaps interestingly, is that you take that Python straightforward traversal, and you just do that in NumPy. So you just take the Python code and you just compile the Python code and do that. Yeah, you get orders of magnitude increase. But then doing this array-oriented way, doing a fully compiled thing is better than doing the array-oriented thing with NumPy, whether immutable or mutable in either case. Mutable is a little bit better. Because in these cases it's running over the whole arrays every time. And there's this bottleneck of getting data from RAM into the CPU that the compiled version does better. But then look, the JAX solution is just taking exactly the same code as the NumPy and just wrap it with, jax.jit. And so the JAX is taking this array-oriented code, this array-oriented way of thinking about doing everything at once, and compiles it so there's not running over the same arrays over and over. And it does better than what scikit-learn itself does. Where you get this little, this extra bit of performance is scikit-learn has to be pre-compiled, probably some C functions. Boy, come on back. Okay. Where are you? What am I looking at? Okay. Probably some C functions, but the C functions have to run over arrays where it doesn't know how large the array is. So while it's doing a for loop of the array, it's always having to check, am I at the end of this? JAX is able to do loop unrolling and all sorts of things that compiler tricks that you get to do if you know up front exactly how large the array is. So it's squeezing that little extra bit out. Okay, so that is the solutions. Yeah.
For using NumPy and JAX, is there any penalty like for the first time you run it?
Yeah. So the question is, if you're using NumPy or JAX, is there a penalty for the first time you run it? Absolutely. Yes. Because the first time you run it, it compiles, and often the compilation can be, can take quite a bit of time as well. In all of these performance tests, I always run it and then do the performance test afterward. Yeah. Yeah.
I have two questions. So the first one is regarding the immutable in place.
Yeah.
Which is tiny. And I would expect the immutable, because it has to request memory for every single rate to be slower. Does that mean intuitive way to think about why they're roughly the same?
Sometimes things matter more than sometimes. Oh, the question is, the immutable and mutable, why are they so close to each other? Because often if you get to reuse the same memory and you don't have to allocate new things, and you don't have to look in new places in RAM all the time, you can do better. And the question is, why isn't it much better? I can't actually hear. Oh, okay, that's right. And actually, I don't have a good answer for that. It is a little bit better, but sometimes this makes more of a difference than other times.
Okay. And the second question is, so if you have any knowledge or idea how is this implemented in libraries, because you told me right now to write a decision tree library, write XGBoost, write something like this, I would probably try to have everything compiled and go like recursively walk, but in a compiled language,
Yeah.
and just explore the API previews. So what do those libraries typically do? What's the
Yeah. So
how do they think?
So the question is, what do the libraries typically do? How do they usually work? Definitely, they precompile. They would, like scikit-learn has got some precompiled C, XGBoost, probably C or C++. And do they use an array-oriented method, or do they use recursively walking down the tree? I'm not sure. I've not opened it up and taken a look. But this NumPy fully compiles, ahead of time, and it uses the recursive walk. And this is a factor of like 2 or more. I think that scikit-learn is doing something a bit smarter than just doing a recursive walk. It might be doing something very similar to what I outlined above. But it's fusing operations, something you can't do in pure NumPy. And it's not able to take advantage of knowing exactly how large the arrays are as a compile time constant, as JAX is. So this is my explanation for the differences in performance. But as for what exactly it's doing, you have to open it up and take a look. And I think that XGBoost is faster than scikit-learn, so it might be doing something smarter. Yeah. Okay. Any other questions? Because we'll be switching topics and we'll be talking more about JAX, which is maybe not a switching topic. Okay. Peter? I'm going to close all of these, and you probably should do this as well. Kill your old kernels whenever it comes up. And take time as you need. I think this is more important than lecture 4.
Mm-hmm.
You have a working system?
I hope so. Let's see.
You need the microphone adjusted?
Okay, I hope you can hear me well. I want to talk a bit more about JIT compilation, because that's how you basically squeeze out the last bit of performance when working with arrays in Python. And in the last lecture, you've seen that this concept of fusing operations is really powerful, because otherwise, let's say you do plenty of element-wise operations like adding +1, taking the square root, doing something else. If you do this in NumPy, you will basically the compiled loop run over the array, do +1. The next step, it will run again over the array and do the square root, and so on. And in principle, you want to do this in one loop, because it doesn't make sense to do this, especially for element-wise operations, to have this loop multiple times. And you can get rid of these first intermediate arrays and also these additional loops by fusing these operations. And this can be done with JIT compilers in Python. And as Jim already said, JIT stands for just-in-time compilation. And it's basically compiling code while you're running already your Python code. And this is really powerful because it can compile the problem to exactly match your data and optimize for your data and exactly the arrays that you're currently working with. Whereas it's usually not as trivial with ahead of time compilation, because maybe you first need to read data from disk and you don't know what the shape is. And two libraries I want to talk a bit more about is NumPy and in particular JAX here. I'm not sure how old NumPy is, but I guess a bit older than JAX. I think JAX is rising. 2012, okay. I think JAX started in roughly 2018 and just in the last few years really caught up as a rising star in the ML and AI scientific computing. So first I want to start by doing some imports here. Actually. Okay. So we're importing NumPy, JAX, the drop-in replacement from JAX for NumPy. So this has this JAX.NumPy submodule. Then we're setting to double precision and to use a CPU. And we also use number. And one thing we can have a look at is with JAX, we are just using a single CPU device. So this is just running on one CPU, where JAX has the potential to run also multiple devices. And now let's have a look again at the quadratic formula. where we basically set up some data and have this quadratic formula from part 2. And when we run this in the NumPy case, we get roughly 166 milliseconds. Now we can write this basically using number.jit. I think before we saw number.vectorize, but this is more explicit, where you basically run or implement a for loop and do each of these element-wise operations on each element. So this is I would say, a bit more explicit way to do this kernel fusion, because you're actually doing it by hand. So we first allocate our output array, and then we loop our array elements and set the output by applying this quadratic formula to each element. And now I'm splitting this timer here in two parts, where the first one is just running once with n minus n1. And then I'm running it again, the same function, but multiple times. Oh, cool. Oh. Forgot to. So this one took 238 milliseconds. Let's run it again. No, yes?
The first one did a compilation.
Yes.
Yeah.
That's exactly what I wanted to show. That's why I splitted it, because the first one is 4 times slower, because it actually did include the compile time. Whereas in the next iterations, it basically picks up the compiled one and runs it again. And yeah, there's basically both libraries have this internal compilation cache, which if a function is already compiled, you can look it up in the compilation cache automatically and do not compile it again. Now for the JAX case, we can implement this again in an array-oriented way, but I will also basically hand over the NumPy arrays to JAX. And I will run this again in 2 steps. And I'm also adding here block until ready, which I quickly explain. This is basically because JAX dispatches computation asynchronously. So basically, running this function, it run it on one thread, and the rest of your program continues on a different one, for example. That's how JAX makes a lot of use from multi-threading. What you can see here is that well, compilation time was faster, but I would say that this doesn't matter too much. But the runtime is now 24.1 milliseconds, where before we had 52.9 for number and 166 for NumPy. And yeah, so we saw that first time compiling something is taking longer, because that's the compile time, and afterwards the compile function is cached. I'm not sure about the caching from number, but for JAX it definitely looks at the inputs of the function. So it depends on the D types and the shapes of the array, and uses this metadata, so to say, to cache, to create a cache key for the compilation cache. But JAX is roughly 2 times faster, right? We had 59 versus 24.1 milliseconds. And one big reason why JAX is, in this case here, faster is because it's quite aggressive in the resource consumption. It tries to use as many threads as it has access to. And we did not restrict this instance to have only one available. Yeah, where number is basically by default single-threaded, but you can use multi-threading when you're using this parallel equals to true in the number.jit decorator. So if you add this parallel equals to true to the just-in-time decorator, and you change the range to a number.p range, which basically makes it aware of this can be multi-threaded. We can run this again. And we got quite a lot further down to match almost JAX's performance. But it's still not exactly on par. Actually, I've done this also locally on my MacBook, and I have a few more threads available, and I got both to be roughly on the 2 to 3 millisecond regime, and this was really on par when I run this locally. One thing that you may have noticed in these two examples was that both libraries force you to write code in different styles. So when number, let's zoom out a bit. When number basically forces you to write imperative code, if you do only, let's say, element-wise operations, you can also use number.vectorize. But in principle, number encourages you to write really for loops over arrays and do explicit things per element. Where JAX doesn't really encourage this, you really want to stay with the array-oriented syntax. There are, however, ways where you can also loop over elements in a compiled way, but yeah, they are usually much less efficient. And you can think about this with this figure, where on the left you can see imperative code, explicit for loops, or vectorized, like array expressions, and then if they're slow or fast. And in principle, they can be categorized in a way where Python is on the bottom left, it's imperative and slow. Number is imperative but compiled, so it's fast. And NumPy and awkward array, which you will see in the next part of this lecture, they are vectorized and fast, but usually not as fast as JAX, because there we have a just-in-time compiler available in addition. And I want to showcase a bit more how this JIT compilation work in practice with the example here of JAX, because first of all, I'm a bit more familiar than with NumPy, but also I think it's a bit more instructive because it's a bit more readable than looking at bytecode analysis. So what does JAX.JIT actually do? And it can be decomposed into 4 steps. The first step is basically we stage out the computation of a JAX.JIT decorated function into a new program. And this new program has its own language, its own programming language, which is called the JAX PR, the JAX expression, which is an internal intermediate representation. The second step is we have this JAX expression, which is like a symbolic representation of the program. It's actually just text. You can imagine it as a text file. And we lower this to another language, which is called stable HLO. And this one is just the language that the XLA compiler uses. And then the third step is to compile this program. And the fourth step is to execute, of course, the compiled program. We can have a look at these steps individually. So step 1 is basically we're creating this first intermediate expression called JAX PR. We do this with tracing. So we have our JAX-JITted function, then we call .trace on it with the input arguments that we would actually call if we would run it. And then we have our trace representation of the program, and we can look at this intermediate representation. And this is how it looks like. Tracing basically works by replacing these input arrays by arrays that don't have any data, but they just have a d-type and a shape. And every operation that we do on this is just returning us another tracer. It doesn't, if we negate something, we just get back a new tracer with the same d-type and shape, but because there are no values, we cannot negate them. And that's basically how we can record every operation in a program and represent this in this intermediate representation. And one thing that may look similar to you is basically how does these operations look like, because if you remember the pedantic formula from the last part, it's completely equivalent. So first we have our inputs, d-type double, and I think 5 million elements. And then the first thing we do was negating b. And if you look at the pedantic quadratic formula, this was also exactly what we were doing in NumPy. Then we were squaring it, and here we're doing an integer power with to the power of 2 onto b. So same what we're seeing in the pedantic one. We're multiplying it. We're multiplying a with 4, so it's also 4 times a. Then we're multiplying the output f and c, this input, and this is basically the multiplication of our temporary variable 3 and c. And you can basically go through this whole computation, and you will see this lines up exactly. Like these operations that we see in this symbolic representation are exactly the same ones that we do here line by line in NumPy. Now the next step that we're doing is basically translating this first intermediate representation into the actual one that our compiler's understanding. This one looks a lot more complicated, but if you look closely, you'll see they are still the same operations. So first we have a negation of argument 1, then we have a multiplication, then we allocate this constant of 4, and then we multiply it at some point later here. So it's just different, so to say, programming languages to represent the same computation. But this one is understood by the XLA compiler, so we can compile it. And we can also have a look at the compiled program, which is even more complicated. So I will not go in depth here. But you can see there are already some keywords that are interesting for us. Like it did some fusion, apparently. And then we can run this compiled program and get out basically our results. There are some limitations to both approaches to JIT compilation. And I first want to show a few from NumPy and then also a few from JAX, because JIT compilation is not something you get for free. There are some caveats you have to keep in mind. And the first limitation from NumPy is something that was limiting me most of the time, which was basically that you cannot JIT everything. All the types that are going into a NumPy compiled function or that are inside a NumPy compiled function, they need to be understood by NumPy. So you cannot use a simple dictionary, for example. So here I have this function that sums the values of a dictionary. So I'm allocating an output that I accumulate into. I'm looping over the values of my dictionary, and I'm summing them up. And then here I'm calling it. Let's see if that works. And it gives me the error. This failed because I cannot determine the number type of this class dictionary. So NumPy is rather limited in the sense what it understands. It does work well with arrays and like these scalars like floats, but other data structures that are built in are not necessarily understood. In this case, there is, of course, a workaround. There's a number.dict, as far as I know, which behaves and looks like a Python dictionary, but just an example, you cannot use this one.
The special number dict
That's what I meant.
knows the types, it knows the key types and the value of type.
Okay, yeah.
That will be the compiler.
Yeah, just to repeat this, so the number.dict knows additionally about the types of the keys and the values. Okay. Some limitations about JAX. And as I said before, everything is figured out through these tracing steps. And yeah, we're just running it with these shallow array objects, no data, but just metadata. And that lets you JIT compile all of Python. So you can, inside of your JIT compiled function, even SSH to, I don't know, some different machine and do something there. But you can't JIT compile on data-dependent operations. If you do something that depends on a numerical value of your array, that doesn't work because the tracer has no access to them. It only has access to shapes and d-types. So I have this accumulate if function that I JIT compile. First I will turn this off. And now I'm doing an if condition. First I'm doing an if condition. If any of my values of the array is larger than 3, do a sum operation, otherwise do a product. Now I'm calling this on this 1, 2, 3, 4, 5 array. First, let's have a look at the error. It says it doesn't work because there's a tracer bool conversion error. And what that means is it was trying to call .any on this, but that doesn't work for a tracer because it doesn't have value. So we cannot compare it if it's larger than 3 and check if this is true or not. It's impossible to convert this to a Boolean. And I'm adding here a print statement because the first time we're running it, we can print actually something. And what we're seeing here is there's a shaped array that we're putting in, and it doesn't know about the values. It doesn't print them. It only knows about the d-type, which is float 64, and the shape, which is 5 elements. But yeah, it doesn't have access to the numerical values 1, 2, 3, 4, 5. Now, another limitation is that at each step of the tracing, it needs to figure out what the output shape is. Just let me scroll up a little bit to our program here that we inferred through tracing. At each of these output steps, if we negate B, we still know the shape of it, of the output. If this is not guaranteed anymore, JAX doesn't know what kind of array it has to allocate or work with in the next steps. So this is something that just is not allowed to do. And we can emulate this behavior by basically, we're summing up all the values that are greater than 3. So first of all, we're selecting all the values that are greater than 3. Then we're masking our array. And here's the trick. Here's the point. We do not know what the output shape is because as I said, this is a tracer. It doesn't have access to it, so we cannot determine the output of the output size of this array. And then we're summing this up. Now, when we run this, we get another error because, as I said, this was not clear what the output shape was. And then I think this is basically the last thing that is quite dangerous to think about JIT compilation. It has something to do with the compilation cache that I mentioned earlier. And this is that impure functions are dangerous with JIT compilation. And this works as well with NumPy and with JAX. So let's say we have this global variable that determines if we're doing a sum or not, and we set it to false. And then we have this accumulation function that takes an array and sums them up if the global variable is true. Otherwise, it calculates the product of them. And now, let's run this with this 1, 2, 3, 4, 5 array. And first, do sum is set to false, so we're doing actually the product. But afterwards, we're switching this on to true. And in both cases, we're getting back 120, even though here we set do sum to true. And that's because the program was compiled, or a function was compiled, at the time when do sum was false. And when you look up the compiled function in the compilation cache again, well, it doesn't depend on do sum as its input argument, so it will pick up the same precompiled function, and that was compiled with doing the product and not the sum. We can see the same actually also with JAX. Maybe we're having the same program, but now I'm JIT compiling it here with JAX.jit. And that has the same problem. So here, also after switching it on, we're still getting the same output result, although that should have been something else. And yeah, because I think in the JAX case, it's easy to have a look at this JAX expression. It's also easy to look at the compiled program or the trace program. And here we see the program that we trace through. It has this reduced product, and it doesn't have any sum. It's also in the lowered version. There's a reduce with a multiply, but there's no sum. So when we push this to the XLA compiler, it never knows about the summation. Before going to the exercise, I also want to talk a little bit about JIT compilation for GPUs, because this is very different for NumPy and JAX. In the NumPy case, NumPy exposes basically a submodule that's called number.cuda. And that is basically, yeah, you can implement the same semantics, how to write CUDA kernels in Python as you would with the CUDA C library that's provided by NVIDIA. So, for example, this matrix multiplication kernel, we can call this CUDA.jit. And then you have to care about the grid sizes and the thread indices by yourself. And you have to keep in mind the GPU programming model in order to properly write this. Whereas in the JAX case, JAX can run this on GPUs as well as on GPUs, and by just using the array-oriented programming paradigm. And that's because these previously shown symbolic operations in the JAX expressions, they are just calling different functions. In the CPU case, they just call CPU compiled some kernels, for example. And in the GPU case, they will just call the GPU version of it. So if you JIT compile this matrix multiplication here, that is just this add operator implemented, then it can run either on CPU or GPU, and it depends on where your data lives. And you can control this by having a look at your devices that are available on your system. And then you can explicitly move data to a device. You can do this, for example, by using device put. You can move this array of 10 elements. You can specify the device here, and JAX.devices gives you a list, so you can choose. Here in this case, this is the first one. And after doing this, you can check with the .device where your array lives. Okay, and yeah, now we can go to the project that you find here. And yes, question?
Yeah. So the question is, so how do you speed up JAX from running it versus running bookkeeping? Because for tracing, you're limited, you can't run conditions, for example, but I believe TensorFlow with its graph mode does support it, just splits up the graph and there's a condition or something. I'm also under the impression that TensorFlow with Torch compile and compile them in a way with kernel. So how do you speed up JAX in this case? Because in machine learning, you may want to run a data.
Yes, there. Okay, for if conditions, you can always use jnp.aware, where you basically evaluate two different things depending on a condition. In practice, this actually runs both paths, and it just merges basically outputs back. There are, however, also some primitives that you can use from JAX that are, I think, in the lex submodule. And there's cont, where you can basically write a condition, and then it depends on if true or false. I think there's also switch for switch case. If there are more if condition-like things, I don't know. But there's also for loops, there are loop primitives, like there's the for I loop, or there's a while loop. And these are pretty handy to use usually, because if you write Python functions, if you think about this, when a tracer runs through it, it will collect everything it does in the for loop in Python. Basically, the tracer unrolls Python loops every time. And that can become very costly for compile time. If you have a loop over 1 million times and you do a heavy computation inside, the compile time will explode by 1 million. And when you use these loop primitives, they reduce that factor. So yeah, you can get around this. I wouldn't say necessarily this speeds things up, but it makes it possible to run them. Any other questions? Okay, then I think we can go to the project. I think we have 20 minutes, right, usually? Then let's say until 11:05.